Welcome back to the second part of Pre-Calc 2.5 notes. We're continuing to find the zeros of polynomials. So taking a look at our next example, if I wanted you to find the zero of this degree 3 polynomial, we may try to factor it. And what I'm noticing is, since it's 4 terms, I'll try the grouping method. But the grouping method is not going to work because I won't get the same set of parentheses. So if I can't factor it, again, that's when we want to use the rational zero test. And the rational zero test would say take the factors of the constant, which is a negative 10. So it would be 1, 2, 5, and 10. Again, we would consider both the pluses and the minuses. And we would divide that then by all the factors of the leading coefficient, which is just 1. So in this case, just plus or minus 1. So that leads us to then try 1, 2, 5, and 10. And again, they're negatives as well. So once we have our list, then we want to take a look at our graph to see which one of these, really 8 different choices, appears to be a 0 on the graph. Now I know that it's a degree 3 polynomial, so that means I should have 3 zeros. But as I'm looking at my graph, it appears that I only have 1. It looks like the graph touches right here at 2. So how do I come up with my second and third 0? Well, most of the time, if it appears that your graph only has 1 0 and it should have 3, it probably means that 2 of those zeros are going to be imaginary numbers. And so I know that if it's a degree 3 polynomial and I can take out one of the zeros, I can factor out basically one of my x's, then I get a degree 2 polynomial that I can solve by using the quadratic formula. So that's the route that we're going to take here, is that we'll have to use the quadratic formula to help us when we're all done here, after we pull out actually one of the zeros. So going back to the graph, we've got a 0 at 2, so let's verify that that works out by using synthetic division. So I will drop down the first term, which is a 1, multiply by 2, add, and I will get negative 4, multiply, I'll get negative 8, add, I'll get 5, multiply, I'll get 10, which is what I wanted, because then I have a remainder of 0. So that means that my 2 divided evenly into the polynomial, which means that it's a 0. So my first 0 is x equals 2. And then, like I said, since this was a degree 3 polynomial, that means this answer is degree 2, and since I don't have any other choices that I can pull off of my graph, I want to try to factor this or use a quadratic formula. So since this is a degree 2 polynomial, and I can't come up with any factors that multiply to be 5 but add to be negative 4, I've got to use the quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So in this problem, a is 1, b is negative 4, and c is 5. So we'll plug in negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2 times 1. So simplifying this, I know negative 4 is positive 4. I know that this is going to be 16 minus 20, so that'd be negative 4. And I know the square root of negative 4 is 2i. And then I can divide each of these individually by 2, and I'd end up with 2 plus or minus I. And so that's going to give me then my second and third zeros. So again, to kind of summarize what we did here, I tried to factor this. That didn't work. So then I looked at the graph, and I could say from the graph it looked like 2 was one of the zeros. So after I confirmed what the possible rational zeros were, I tried 2. I got that to factor out evenly, so it gave me a remainder of 0. And then, since I don't have any more choices from my graph, that led me to believe that the other 2 zeros that I had would be imaginary numbers. So I knew I was going to have to use the quadratic formula because this wouldn't factor. And of course, this number down here, 2 plus or minus I, is an imaginary number. So I get my 3 zeros that way. Again, using and taking a look at the graph is going to be a great way for us to get started using synthetic division. And then once we've done that, we can either try to factor or, in some cases, use the quadratic formula to find our remaining zeros. In our next example, we're asked to find the zeros of the degree 3 polynomial, so that means I know I should get 3 zeros altogether, but I'm given a 0 this time. I'm told that 5 plus 2i is a 0. So whenever I'm told that an imaginary number is a 0, then I know that its conjugate, in this case complex conjugate, would also be a 0. So I know that the other 0 that I have is 5 minus 2i. So again, I'm going to come up with 3 zeros. So if I'm given 1, again that is a imaginary number, it comes in pairs, the zeros come in pairs, and I would have 5 minus 2i as a 0. So far I would say that x is equal to 5 plus 2i, x is equal to 5 minus 2i. I still have to come up with that third 0 then. And the way that I can find that is I know that these zeros should divide evenly into my polynomial. Now because they're imaginary numbers, they're not going to divide evenly in, but when I multiply them together, they would divide evenly in if I write them as factors. So let's write the zeros as factors. And remember, the way we do that is we do x minus each of these. So x minus 5 plus 2i, and x minus 5 minus 2i. So now if I take the time to multiply these together, that answer, which will have no more i's in it, will divide evenly into here. So if I try to divide just an x minus a 5 plus 2i in here, I'm not going to be able to get that to divide evenly because of the imaginary numbers. But by multiplying these together, I can get the imaginary numbers to go away. Easiest way to multiply these together is to make a chart that looks something like this. Take one of the polynomials and spread them out horizontally, take the other and spread it out vertically, and then you can go through and you can make some lines on here that will help you address what you're multiplying together. Okay, so if we start multiplying together, we get x squared minus 5x plus 2ix minus 5x plus 25 minus 10i minus 2ix plus 10i, and then minus a 4i squared. Now one of the nice things about multiplying complex conjugates together is any term that has an I in it is going to cancel out with another term. So for example, my plus 2ix and my minus 2ix cancels out, so will my 10i and my negative 10i. Now remember that I squared is the same as negative 1, so really what you have here is negative 4 times negative 1, which really makes a positive 4. So I'm going to cancel this out and put a 4 in that box, so I know that there's really a positive 4 there instead of a negative 4i squared. And now if I go through and I figure out what I have left over by combining like terms, I'd come up with an x squared. Cross that off because there are no more like terms with it. These two are like terms. They make negative 10x. Cross them off so I don't use them again. And then your 25 plus your 4 makes 29. So this polynomial should now divide evenly into my original polynomial. So what I'm going to do is set it up with long division. I can't use synthetic division here because this is a degree 2 polynomial, and synthetic division only works with degree 1 polynomials. So remember the process is, what do you have to multiply x squared by to get x to the third? Well, that'll just be an x. And now we times all three of these by x, and we write that answer underneath here, and then we subtract. So this time the first term should cancel out. I'm going to get a 3x squared minus 30x, drop down the 87, and again ask myself, what do I have to multiply an x squared by to get a 3x squared? that'd be a positive 3. So when I multiply all these by positive 3, I get 3x squared minus 30x plus 87. When I subtract, what will happen now is every single thing will cancel out. And that's what I want to happen, because I know that since these were both zeros, and when I multiply them together I ended up getting this, that means that this should divide evenly into my original polynomial, which means I should get a remainder of 0. So that now I can figure out what my third 0 is by setting this equal to 0. So x plus 3 equals 0 would mean that my last 0 would be negative 3. So again, if you're trying to go back and figure out what are the steps when we solve a problem like this, the first thing you want to do is recognize that you've got to come up with your other 0. Then write those zeros as factors, which I did. And then take the time to actually multiply those factors together in your table, which would give you this answer here. And then divide that answer into the original polynomial. And the last thing you could do then is set that answer equal to 0 to come up with your third 0 for this specific example. Don't forget though, if you see an imaginary number, that it would come in pairs. Also, if you had, for example, if you're told that one of the zeros of your polynomial is 1 plus the square root of 7, that's an irrational number, then you also know that 1 minus the square root of 7 has to be a 0. So imaginary numbers come in pair, but so do irrational numbers. So when you're given the fact that one of the zeros is an irrational number, you know that its complex, or that its conjugate, in this case 1 minus the square root of 7, would also be a 0. So that's just a side note for another problem. Obviously that doesn't have to do with this problem, but complex numbers come in pairs in terms of their zeros, and so do irrational numbers come in pairs in terms of their zeros.